What has a higher specific gravity, milk or water? Does it matter whether it's whole milk or fat-free milk? Stick around if you want to find out. To answer this question, we need to remember the definition of the density of objects, which is the mass divided by the volume. And for liquids like water or milk, the specific gravity is the density of the liquid divided by the density of water at a reference condition. Easy then. Now, when we're doing any type of experiment, we want to make sure we try to eliminate or at least reduce all of our systematic errors. An easy one in this experiment is the weight. We can check our scale using some calibration weights. These weights are specifically designed to be very accurate, and that way they can be used to calibrate your scale. If you're new here, I'm Cody, and I make videos about science, technology, engineering, and mathematics through experiments that you can do at home. But I like to take it a step further and actually do some of the data analysis of the experiments that we do here. If you like learning about these things and you want to bring your textbooks to life, join me. Subscribe to the channel and check out the other videos we have. We'll start with 100 grams. Here it is. And if we place it on the scale, let's go ahead and try 20 grams. This is just a little guy. Excellent. So, we see that our scale is actually quite well calibrated and very accurate as far as the weights go. Now, we can find the weight of our sample, whatever it may be, water or milk, by first filling this up to an appropriate volume, weighing it, then subtracting off the weight of the dry cylinder, leaving only the volume that we're finding the mass of. We need to find the density of water at 4 degrees Celsius, since this is the denominator of our specific gravity equation. The U.S. Geological Survey has an ice table showing water density at various temperatures, and the value we need is conveniently 1 gram per centimeter cubed, or milliliter. In conducting our experiment, we start by measuring the temperature of our sample, and we can see that the milk is approximately 12 degrees Celsius, which is about 53 degrees Fahrenheit. I'm using the light source behind the graduated cylinder to try and better make out the meniscus of the sample, and then use the eyedropper to remove bubbles and add very small amounts of milk. For this fat-free milk sample, look at how much more visible the meniscus is with the light source behind it. Here are our initial results, where we conducted the experiment for each milk type 4 times at varying volumes. It's hard to make out the difference in relationships, so let's focus on the mean or average values of the 3 normal milk samples. Here we see that directionally our hypothesis is looking good and that skim or fat-free milk has a higher specific gravity than whole milk. But how good are our results? Do they actually match the published literature?
Let's start by looking at one of the most cited journal articles for milk density, published in 1955. We see the range is approximately between 1.021 to 1.035 grams per milliliter. But this is a pretty old result, so let's check out a result from 2009, from the Book of Advanced Dairy Chemistry. For whole milk, the range is 1.027 to 1.033 grams per milliliter, whereas the range for skim milk is given as 1.032 to 1.036 grams per milliliter. And since we are taking the density of water equal to 1 gram per milliliter, these are our respective specific gravity ranges. Based on the results, we seem off by around 2 to 5%. Alright, let's redo the experiments for skim and whole milk, but change the way we measure to try and increase accuracy. We know the scale is pretty accurate, but our volume measurements can be improved. Using a larger graduated cylinder with a larger sample of milk makes it slightly easier to see the meniscus and also reduces the error when evaluating the sample. Here are the results for our higher accuracy experiments. Skim milk has an average or mean value of specific gravity of 1.034 versus whole milk's value of 1.025. The gray region shows the range of values from our published references, and we see that our results are within the range.
Not too bad, given our difficulty in identifying the meniscus of whole milk. It seems likely we overestimated the height or level of the meniscus, which led to a larger volume and correspondingly a lower density, and therefore a lower specific gravity than the published results. But our data shows sufficiently that the specific gravity of fat-free or skim milk is actually higher than that of whole milk. If you enjoyed this video, give it a like and be sure to subscribe to our channel for more content like this. And until next time, cheers.